About a month ago, I released a video explaining how telescope focal length, field of view, and sensor properties all interact and influence your final image. In that video, I mentioned there would be a part 2, a practical follow-up showing how to compare two telescope setups to determine which one is more efficient for capturing a specific target. Well, today's the day, and for those of you who enjoyed one of my very first videos, Are Fast Telescopes Really Better? Demystifying Astrographs, today we'll be expanding on the concepts we covered last year, adding a few theoretical concepts, and introducing a brand new tool to directly compare two complete imaging systems. So let's dive right in. My name is Luca, and you're watching the Space Koala. One of the key takeaways from part 1 was that it doesn't make sense to compare two telescopes or their speed without knowing which sensor they'll be paired with. And the same goes the other way around. Comparing two cameras without specifying the optics makes little sense. So how do we compare two complete imaging systems in a fair and practical way? One of the most effective methods is to ask, how long does it take for each setup to reach the same final image? And by same image, we mean exactly the same final field of view and image resolution. That's important because it wouldn't make sense to compare two images with the same field of view if one has twice as many pixels. The level of detail would be completely different. And likewise, comparing two images with the same resolution but radically different fields of view is equally misleading, because one would be showing a much smaller portion of the sky in far greater detail. To make a fair comparison, we need both systems to produce images that are identical in framing and pixel count. Only then can we truly compare how efficiently they reach that result. That's what we'll be doing today. However, when comparing different systems, achieving the same final result often requires some form of processing, either to match the field of view or resolution. To do this, we may need to apply techniques like resampling, drizzling, cropping, or mosaicing. I know many of you are already familiar with these, but I'll go through them briefly to make sure we're all on the same page. The first technique we'll look at is binning, also known as resampling. This involves averaging adjacent pixels into a single superpixel to improve the signal-to-noise ratio. Typically, we use grids of 2x2 or 3x3 pixels for this. When done in post-processing, this is a specific type of downsampling that uses an integer factor. If performed in camera, this process can vary dependent on whether it's a CMOS or CCD sensor, and in the case of CCDs, true hardware binning may offer different advantages, though we won't go into those details today. What's important to understand is that binning reduces resolution. That's the intended effect. This can be very helpful in many cases, but it is something to avoid when fine details are critical, as those will inevitably be lost. The next technique is drizzling, which is essentially the opposite of binning. Instead of reducing resolution to boost signal, drizzling aims to increase resolution by reconstructing image data from multiple exposures. It is particularly useful for recovering sub-pixel detail, but only if your optical system and acquisition method support it. Here's how it works. First, we define a new, finer grid. This will be the resolution of our final image. Then we take our first exposure and drizzle its pixels onto this grid. The process gets its name from this idea. Each piece of data is like a droplet of water being drizzled into a pixel-sized bucket on this new grid. The droplets, our signal, can be shaped using different kernel functions that define how the information is spread. At this point, we technically have a higher resolution image, more pixels, but not more information. We've simply resampled the image data. Now let's add a second exposure. If the second exposure is exactly aligned with the first one, we gain nothing. But if it is slightly offset, for example, if the data was dithered, Things get interesting. When we drizzle the second image onto the same grid, its pixels land in different places. As we combine the two, we start to fill the new shades and values that weren't truly captured in either image alone. And that's the key. Drizzling only works if your images are slightly misaligned from each other, which is why dithering during acquisition is essential. With just 2 images, we already begin to recover more detail. With 15, 20 or more well-dithered subs, the improvement can be dramatic, assuming your optical system is capable of resolving it. It's also worth noting that drizzling is computationally expensive and takes up a lot more storage and processing time. But when used correctly, it is a powerful tool to improve resolution without interpolation, making it especially valuable in undersampled setups. If you're unsure what undersampling means, or how to tell when it's happening, or how your setup affects the spatial frequencies you can resolve, I covered all of that in detail in the first part of this video that I will link in the description. So far, we focused on image resolution, but now we'll look at how to match the field of view between 2 different imaging systems. The simplest method is cropping. There's not much to explain. We use this when we want to restrict the field of view. It's the easiest operation. We just discard the parts of the image we're not interested in. The main drawback is that we're throwing away data that we already acquired for no reason. Finally, we have the opposite situation when we want to enlarge our field of view. This is where mosaicing comes in. To capture a larger area of the sky, we take multiple panels and combine them into a single image. It's essentially like creating a panorama of the sky. One important thing to note is that for mosaicing to work well in post-processing, the individual panels usually need to overlap, which reduces efficiency. And if we're shooting under suboptimal skies, stitching the panels seamlessly becomes even more difficult due to gradients and other artifacts. On top of that, mosaicing requires better session planning to make sure we capture all the necessary panels. That covers all the processing techniques we need to fairly compare 2 telescopes. So now let's ask the big question. How long does it actually take to capture the same image using a faster versus a slower telescope? It's a common belief that a faster telescope will always let us capture the same image in less time. And last time we introduced the concept of the f-number, which, as a reminder, is simply the ratio between a telescope's focal length and its aperture diameter. It's a useful metric for many things, but when it comes to evaluating a light gathering capability, there is one more factor we need to consider. Many telescopes, like Newtonians and other reflectors, have a central obstruction. That means there's an area in the middle of the aperture that doesn't collect any light. To account for this, I'm introducing something I call the effective f-number. It's calculated almost the same way, but instead of dividing the focal length by the physical aperture, we divide it by the diameter of a circle whose area equals the actual light gathering area of the telescope. That is the total aperture minus the area blocked by the obstruction. In short, the effective f-number reflects the true efficiency of a telescope by factoring in the loss of light due to obstructions. But what does this mean in practice? Let's look at a few examples. Take the ASCAR telescope with a native focal ratio of f5.6. If we add a reducer to make it faster on paper, the actual light gathering doesn't increase because the physical aperture at the front remains unchanged. So while the focal ratio decreases, the effective collecting area does not improve. Next, consider the popular Celestron RASA 8. On paper, it has an impressively fast focal ratio of f2, but once we factor in the central obstruction, the effective focal ratio becomes f2.2. That's a small difference, not a deal breaker, but still worth noting. Now, compare that to something like the plane wave delta rho, another well-known astrograph that advertises a fast f3 focal ratio. However, if you've seen one, you'll know that it has a massive central obstruction. Once accounted for, the effective focal ratio drops to f3.6, a much more substantial difference that impacts overall imaging speed. When comparing the efficiency of different systems, we should focus on their effective f ratios. That's why throughout our examples, we've assumed that all the telescopes are refractors, so there's no central obstruction and no loss of light from the aperture. This way, we can compare systems without that additional variable influencing the results. In the examples that follow, we'll make a few assumptions to keep things simple and focused. First, we'll use the same exact sensor with both telescopes, meaning identical sensor size and pixel size. In the case of mosaics, we'll assume perfect stitching with no overlap. We're also not going to factor in theoretical optical limitations like under or oversampling. Our goal is simply to compare the mathematical number of photons per pixel needed to reach an identical final image. For that reason, we are also ignoring the contrast loss effects we've discussed earlier in relation to MTF curves. With those assumptions in place, let's start looking at the actual examples. Let's look at the first example. We have two telescopes with the same focal length of 800 millimeters, and we expose for the same amount of time. The only difference is their aperture. One has a 200 millimeter diameter, making it an f4 system, while the other has a 100 millimeter diameter, making it f8. As expected, the faster f4 telescope on the left produces a much brighter image with less noise, simply because it collects more light. So how can we get the same image using the slower f8 telescope? Would need to expose for longer. But how much longer? Since the faster telescope has twice the aperture diameter and light collection depends on surface area, we need to expose 4 times as long with the slower scope to gather the same number of photons per pixel. So, doesn't this mean the faster telescope is better? Before we jump to any conclusions, let's take a look at example 2. This time, we're comparing two telescopes with the same aperture, 100 millimeters, but with different focal lengths. One is an f4 system, 100 millimeter aperture, 400 millimeter focal length, and the other is f8, 100 millimeter aperture with an 800 millimeter focal length. We're imaging the same galaxy, but the results look quite different. The faster f4 telescope on the left gives us a brighter image, but with less zoom. It covers a wider field of view. The slower f8 telescope on the right captures more detail, but the image is much darker. So how do we recreate one image using the other telescope? Let's start by asking, how can we get the wide field image from the slower f8 telescope? Since we need a wider field of view, we need to create a mosaic. The individual images from the slower telescope are dimmer, but we also know that the fast scope produces a lower resolution result. That means we can bin the mosaic panels from the slower telescope, reducing resolution and improving signal-to-noise. As a result, instead of needing 16 times longer, as raw pixel count might suggest, we only need 4 times as long to match the image from the faster scope. Now, let's reverse the question. How do we replicate the native image of the slower f8 telescope using a faster f4 scope? Here, we also need to do two things. First, we crop the wider field image from the fast telescope to match the smaller field of view of the slower one. That's easy. But to recover the missing resolution, we also need to apply drizzling. And as we saw earlier, drizzling distributes the same number of photons over more pixels, which means the image gets darker. So in the end, there is no time advantage to using the faster telescope in this case. To match both resolution and framing, it takes just as long. We've already looked at what happens when we fix either the focal length or the aperture between two telescopes. Now let's see what happens when we keep the focal ratio the same. In this example, both telescopes have an f4 focal ratio, but they differ in size. One is a 100 mm aperture with a 400 mm focal length, and the other is a 200 mm with 800 millimeters of focal length, so 200-800. Because they share the same ratio, the images they produce have the same brightness. However, the smaller telescope gives us a wider field of view, while the larger one offers a narrower, more detailed view. Let's figure out how to replicate each of these images with the other telescope. First, if we want to match the wide field image using the larger 200-800 scope, we need to do a mosaic. That's familiar territory by now. And because we're trying to replicate the lower resolution image, we can bin our mosaic panels. The key difference here is that the native image from the larger scope is already just as bright. So binning makes each panel 4 times faster to acquire. Even though we're shooting 4 separate panels, each one takes only a quarter of the time, meaning that the total imaging time is the same as with the smaller, shorter scope. Now, what about the reverse? Suppose we want to recreate the more zoomed in detailed image from the larger scope using the smaller 100-400 telescope. To match the narrower field of view, we crop the image. To match the higher resolution, we drizzle. But as we've seen, drizzling spreads the same number of photons over more pixels, making the image darker. So to reach that same brightness level, we actually need to expose 4 times longer. And that's the key insight. Even though both scopes have the same F ratio, it still takes significantly longer to reach the same detailed, bright result with the smaller telescope. So far, we've seen 3 different cases. In the first, the faster telescope clearly performed better. In the second, the advantage depended entirely on the field of view we were aiming for. The benefit of the faster scope wasn't guaranteed. And in the third case, even though both telescopes had the same focal ratio, they performed very differently. This might lead us to question whether the focal ratio alone truly determines imaging efficiency. And the truth is, we can't draw broad conclusions from just a few specific examples. What we really need is a way to generalize this process to compare any pair of imaging systems regardless of field of view or scaling factor, and to properly account for things like inefficiencies introduced by mosaicing. The math involved becomes too complex to keep in our heads, so we need a tool that handles it all for us. And that's exactly what I've built. I'm going to introduce it now, but first, let's run a sanity check by revisiting the 3 examples we just discussed. That way I can show you how to read the tool and what to expect from it. Here we have the results from the 3 cases we discussed earlier. In the first example, where both telescopes had the same focal length but different apertures, we see that the green system, representing the larger aperture, is more efficient across all fields of view. The graph here is structured as a 10 by 10 degree patch of the sky, a very large area. Each point corresponds to a specific desired field of view and is colored according to which system, so telescope plus camera, would deliver more photons per pixel once the images are rescaled to the same resolution. In other words, we're comparing how efficiently each setup fills each pixel with signal for a given final image. If both systems perform equally at the field of view and resolution, the point is shown in yellow. In the bottom left corner, you'll also find the native field of view for both systems. The result is exactly what we saw before. The larger aperture telescope always wins. In the second case, where both telescopes had the same aperture but different focal lengths, the outcome depends on the field of view. For wider fields, the faster, shorter telescope is more efficient, but as we zoom in, the chart turns yellow. That means both telescopes have identical efficiency for those narrower fields, which is consistent with what we concluded earlier. Finally, in the third example, two telescopes with the same focal ratio but different sizes, we see that while there are certain specific conditions where they perform the same, the larger telescope is more efficient in the vast majority of field of view scenarios. Now, let's apply this calculator to some real-world examples using telescopes that I personally own and use. The question is, which of these imaging systems gathers more light for a given field of view? It's important to note that this tool reflects more realistic conditions. For example, it already factors in losses from mosaicing, assuming a 15% overlap between panels. Let's start with an extreme comparison. On one side, we have the C14 operating at f11 without a reducer, and on the other, the RedCat 51 at f4.9, both paired with full-frame sensors. What's surprising here is how many mosaic panels we can cover with the C14 and still be more efficient than the much faster RedCat. That's thanks to the C14's significantly larger aperture and greater light gathering power. Now let's push it further. Let's compare the same f11 C14 to RASA 8 at f2. Again, both using full-frame sensors. In this case, the RASA has the advantage of not only being much faster, but also having a larger aperture than the RedCat, so it performs better in more scenarios. However, even here, there are still areas of the sky where mosaicing with the C14 is more efficient than using the RASA 8 directly. Finally, let's look at the FRA600 refractor versus the RASA 8. Here, the RASA wins across the board. It's larger, faster, and overall more capable. In this case, there's no field of view where the FRA600 can collect more light than the RASA 8. However, if we want to be realistic, we have to acknowledge that we can't actually use a full-frame sensor on the RedCat, and I also can't use one on the RASA. That's simply a limitation of these faster optical systems. Once we account for the fact that these telescopes typically only support APS-C sensors at best, their advantages shrink significantly, especially when compared to something like the C14, which can handle a full-frame sensor without issue. That said, in the case of the FRA600 versus the RASA, even if we consider a smaller sensor on the RASA, it still outperforms the refractor across the board. Finally, let's take a look at some more extreme examples, because that is the direction the market seems to be heading. Fast telescopes are increasingly popular because the lower f ratio sounds appealing, but at the same time, many people try to recover the lost zoom and detail by pairing these fast scopes with very small sensors that have very tiny pixels. So what happens when we try to match the field of view of a large telescope using a fast one with a smaller sensor? Let's compare the RASA 8 with the C14. We try to achieve a similar field of view by putting a very small planetary camera, the IMX715, on the RASA. Even though the RASA is an f2 system and the C14 is an f11, the RASA performs significantly worse in this setup. Using a small sensor effectively crops the image on the focal plane, throwing away a large portion of the light the telescope gathers. We see the same thing when comparing the RASA to the FRA600. Previously, the refractor couldn't compete with the RASA, but once we switched to a tiny sensor with tiny pixels on the RASA, in an attempt to regain zoom, the FRA600 actually outperforms the RASA in nearly every field of view scenario. So what does this all mean for us? We've seen that when paired with the right camera, slower telescopes with longer focal lengths are ideal for capturing fine details in narrow fields of view. Meanwhile, fast astrographs, again, when matched with suitable sensors, are excellent for covering large areas of the sky efficiently. But the key takeaway here is that fast systems come with trade-offs. Faster telescopes often have smaller illuminated circles, which limits the sensors you can use. As we discussed in the previous video, they may require specialized filters, and they are also far more sensitive to focus, meaning you'll need to refocus more often and deal with issues like tilt and collimation more carefully. Most importantly, watch out for the small pixel trap. Putting a tiny sensor with tiny pixels on a fast telescope to try and zoom in cancels out all the advantages of the fast system while keeping all of its challenges, limited compatibility, stricter tolerances, and more demanding filters without gaining any real efficiency. You end up throwing away most of the light you worked to collect. So which is the best telescope? Well, there's no single answer. It depends entirely on what you're trying to capture and what kind of images you want to take. But more often than not, the best telescope is the one you already have. The key is understanding how to get the most out of your setup and how to pair it with the right camera and processing strategy for your specific goals. Because in the end, the speed of your system isn't just about focal ratio. It's about the whole picture, your scope, your sensor, your target, and your technique. It's all a matter of perspective. The tool we explored today is now also available in a more polished, user-friendly format on my website, thespacekoala.com. You'll find it under Tools, Telescope Comparison. It is completely free to use. Just enter the specs of your telescope and camera, and it will help you see which of two optical systems performs better in terms of light gathering efficiency. Feel free to experiment with it. I hope this overview helps clarify the trade-offs between cropping with a faster telescope and mosaicing with a slower one, and how those choices impact your imaging strategy. Let me know in the comments, did I manage to convince any of you that faster isn't always faster, or are you still proudly Team F2 RASA? If you're into this kind of content, telescope comparisons, deep dives into astrophotography theory, don't forget to subscribe to the channel. Thank you for watching, and as always, I wish you clear skies.